My name is Rachael Farber, and I am an ultra-high vacuum surface scientist. So my background was in physical chemistry, and in grad school I investigated the catalytic properties of oxidized metal surfaces, and then in my postdoc I looked at the surface structure of superconducting materials for particle accelerator cavities. And all of those things came together to sort of build up my training in looking at complicated surfaces and their structural and chemical properties. So here at KU, my group has two main focuses. One is looking at fundamental behavior of heterogeneous catalysts, and the other is looking at the material properties of thin films. So for looking at the fundamental properties of catalysts, we make in our ultra-high vacuum setup different oxide surfaces and deposit metal nanoparticles on them. And we study the structural, chemical, and electronic properties of those surfaces because each of those things can impact the chemical activity. And for understanding materials, what we do is prepare a variety of thin films, whether they're self-assembled monolayers or graphene on different metal surfaces. And we study a combination of their structural and electronic properties so we can understand how and why the materials work the way they do. So in my group, we tend to collaborate with people in condensed matter physics, chemical engineering, computational chemists, things like this. We have a collaboration with a computational chemist down at the University of Oklahoma who's helping us understand these oxide-supported nanoparticle systems. We're starting a collaboration with researchers at KU in the chemical engineering department to understand a different system of nanoparticles on an oxide or metallic support for their biomass conversion properties. And we've collaborated with condensed matter physicists looking at self-assembled monolayers. So as a faculty member, my job is to mentor and direct students in sort of their research projects. But in terms of the actual work being done, it's led by a combination of graduate students and undergraduate students. And once they've been trained on how to use the different techniques in my lab, because there's a little bit of a learning curve, you don't necessarily run into them in undergrad lab classes. Once they have that base training, a lot of the students will take the research ideas and go down their own paths to sort of find the next interesting system or thing to look at. So I might come up with an idea or a system that I'd like students to sort of look at, but it's a collaboration between the students and myself to see where the project goes, what the results are going to be. And one of the fun things with our undergrad students is they're given the opportunity to really drive projects on the material side as well as the catalysis side. So it's sort of a collaboration between everyone. Generally, for students that sort of get trained in surface science, there are a variety of research or industry sort of based positions that they can pursue. If you want to go into academia, that's always an option. There's a lot of really interesting surface science work getting done at various national labs here in the US, as well as abroad. And then for industry positions, a lot of people will go into the semiconductor industry. So working at places like Intel is pretty popular. You can go into more instrumentation design because we work with a variety of different instruments in the lab. So the skills that you build up in a lab like this, where it's a combination of experiments, electrical, plumbing, materials synthesis and study, you can sort of go into a variety of career paths.